Now, as we go into topic 6, our last section of chapter 9, we're going to be dealing with functions with radicals. So, back in 1103, we did some functions, but let's just do a little review here. Now, some of the words you may or may not recall were the word relation, and since we're going to do some graphing here, we often think of a good example of a relation as the ordered pair. And when we define the word domain, domain refers to the first element in the ordered pair, which is the x. So the domain would be the x values, and the range would be the second value in the ordered pair. In this case, it's the y. And we said something is a function if the x value is only used once in a series of relations. Okay, so that's just a little quick review as to where we're going. And then we have to keep in mind also something in here, that you can't have a negative value under the radical sign. It has to be 0 or larger than 0. Can't be a negative value. So these are some of the little background things we're pulling in to move on into this section here. So we'll briefly review the concepts of functions and function notation. We did a little bit of that now. Then we want to find the domain and range of radical functions. We want to evaluate radical functions. We're going to graph radical functions, and for those of you that have these fancy calculators, we'll go over that a little bit as well. Okay, so this is what we reviewed, and I see they're doing a nice review here as well. And they're reviewing a function. A function is the x element, or the first element in a series, can only be used once, that value. And we'll see this as we go on here. And remember, we had the vertical line test. And let's just do a little review of this here. Now, the vertical line test we had mentioned was if you have a vertical line and you pass this vertical line over the face of the graph, does this vertical line only intersect the graph in one place as you move it across the face of the graph? Well, in this case, the answer is yes. So this is a function. Now, if we take that vertical line and pass it over this diagram, you see when it gets here, it's going to intersect in more than one place. So this is not a function. Okay? And that's what they're saying here. All right, well, let's continue a little bit. Let's see what they're going to bring us here. Now, they're also mentioning what I mentioned in the beginning, that if you have a radical and the index number is even, then this cannot be a negative value here. Now, if it's odd, it's okay to have a negative value. This is one of the things we mentioned earlier in this chapter. All right. So it has to be greater or equal to 0. But otherwise, if it is an odd index number, you can have negatives under here. So those values of x would not be restrictive. Here, if n is an even number, it has to be greater or equal to 0. If it's an odd number, there are no restrictions. The interval notation would be, it could be from negative infinity to positive infinity. This is all real numbers. Okay, so here they're saying it is a function, and they want you to determine the domain of this. So again, you're taking some notes and writing these examples up, and the rule is you take the radicand and say it has to be greater or equal to 0. So we just transpose that, and on this side it becomes a -3, and we have 2x, and we divide both sides now by 2, and we have x is greater than or equal to a -3/2. Now, if we were to graph this on a number line, which we did back in 1103, this point here is a -3/2. Is this value included in the set? And the answer is yes. So in the old days we'd put like a dot there, but what we do to indicate it's included in the set now is we use a bracket. So a bracket at -3/2, and since it's greater than, and you kind of follow the direction of the inequality sign, it's going to look like so. Now, how do we convert that into interval notation? Well, right from the graph, we're going to use a bracket, our -3/2, comma, and this is going to go out here to positive infinity. And there's what we have. And that's how we solved it, and that's the technique. Whatever's under the radical sign, we equate it to greater or equal to 0, because it has to be greater or equal to 0. We find out what that value of x would be, and then that would be our domain. Okay, let's check this out now. And there it is. Okay, so not too hard as long as you know the technique. Now, for something that's cubed, does it have to be greater or equal to 0? No, because it's an odd index number, this is going to be all real numbers. And again, the key is you note the index number. If it's odd, there are no restrictions. Okay? Again, you're going to write this into your notes, and this is something that as you prepare for a test or use in practice and certify, you have an example of what to do. Now, if they want you now to evaluate a radical function, and keep in mind this is what we call function notation here, and they're giving you this. So what do you do? Well, as we did in, I think it was chapter 6 or so, where we did some t-charting and putting in some values, and then finding out what would f of x be. In a sense, this is your y. Well, you're going to make a t-chart in your notes, and you're going to do the calculations. So when you substitute x with a 7, you get the cube root here of 0, which is 0. So that's what you'd put here in the y column, 0. Now if you put a 6 there, you get the cube root of -1, which is -1. And notice they did some, brainstorming here, some artistry. They picked out numbers that wouldn't be too challenging here. So they picked out a -1. A -1 and a -7 give you a -8. The cube root of -8, again using our tools, is a -2. So we now have some values. And that's how we figured it out. Now, for something like this, for example B, again, you're going to write this down. This is function notation of a radical function. You're going to say x is 0. So 3 times 0 is going to be 0 here. If x is 4, the square root of 4 is 2. 3 times 2 is 6. Now here, when we take the square root of 6, we're going to get a irrational number, and we multiply it by 3, that's going to be irrational. But you get the idea of how to do this here. Okay, so again, you've written this down, you put a t-chart here, and now you're going to put your values. So it's 0 for this. We said this one was 6. This is the protocol for doing it. And now, when you just put this in your calculator, you get this irrational number here, which is the value. And now they're going to ask you to physically graph this function. Now we could have put f of x here as a function equation, but again we're going to make a t-chart. And also, since this is an even index number, we have to see what number do we start with. So, taking a step back then, is when they ask you to graph a function, you have to figure out where would your domain start. So you're going to equate the radicand here to greater or equal to 0. And that's what they're showing. So it's going to start then at a -5. So you wouldn't put a -6 in there, because -6 would make this radicand a -1. -6 plus 5 would be a -1. So it's going to start at a -5. And then you just put some other points in there, and hopefully you pick points that make these numbers nice, although you could possibly use a irrational number as well. So here are the ones they're giving. And again, write these down. You'd pause it, as I would. And then at this point, it makes it a 0. So that's sort of where it like anchors onto your graph. And then using a -4 in there gives you a 1. And then a -3 gives you the square root of 2, which is about 1.414. And if you use a 0, it gives you the square root of 5, which is this. And if you use a 4, it gives you a 9. Square root of 9 is 3. Okay. So you've got a series of points here. So it looks a little bit like this. Now, as you do this in your practice and in your certify, you have a graph, and you're going to put your ordered pairs in there, and then that'll make a nice graph for you. Now, notice the shape of this line, which is so characteristic of the square root of x. So if we just had the square root of x, by the way, that would look like this. But when you have other values in here, like a -5, or I should say that was a positive 5, wasn't it? Then it shifts this over, but it's the same general shape. So a graph that looks like so is usually a square root type of graph. Okay, but you'll have some practice and some experience with this. Now, what we didn't do, and let's go back one here to see this on the graph. So what would your domain be here? And we had done this before too. So domain, where do the x values start? Well, they start right here. So it would be a bracket, and it's -5, comma, to positive infinity, because that's where this is going. But notice it's starting to go up a little bit too. So what would our range be? Well, notice here we're looking for y values for the range. So if we project that over to the y-axis, that's at 0. So it's starting at 0, and then ever so slowly, notice it's going up. So eventually this will go up to positive infinity for your y values as well. So use of the graph is good here to show this. And that's what they're showing here. Okay. Now here they're saying use of a graphing calculator. And again, we don't feature that, but you put this into your graphing calculator, y equals, and then, put the third root in there. Now, to put that in there, you'd have to do it this way, because you can't put these signs in there. So how do you do that? Well, it would be y equals, you'd put this in parentheses, the radicand, 2x minus 3 in parentheses. And you could put all of that in the TI-84 here. But this is to the third root here. So how do I convert this to a fractional exponent? Well, you would use the caret sign, and then you'd put a parenthesis, and then you'd put 1 divided by 3, close parenthesis. So this is how you would put it in to your TI-83 or 84s or any of your graphing calculators. So the key is to convert it from its radical form to its exponential, fractional exponential form here. All right. I think that's what they're going to show us here. Yes, they have to enter that. And then, it gives you some points. And then this is what they look like. So, where square root of something, square root of x look like this, the cube root of x looks like that. And that's sort of what they're showing here. Okay, well, again, I'm not sure how much we're going to be doing of this, but you may have some of it there. And that's what it looks like. Okay, so we kept this one about 20 minutes. Good. And let me just show you the rest of these. And these are the answers. But we're not physically doing them. You don't have to have this in your notebook.